Good evening and welcome everybody. This is Obi-Wan Pez friend Simplex Pachinko. Gonna do some math tonight. Blainlin, yes. Inverse matrix. Always fun. It's one of those things, right? How did people figure out exactly that this thing existed in the first place? And then what form it took and all that stuff. Alright, if anybody has any questions, feel free to drop them in the chat. And just expand this just a little bit. Yeah, alright. It's good enough anyway. Okay. Oh, that actually might have... Yep, that just offset everything. There we go. Okay. Hey, Bit Center. Good, how are you? So we could do something like this. If you want to find an inverse matrix for a given matrix, then what we can do is say, okay, well, we want this such that A times A inverse is going to be equal to A inverse times A equals the identity matrix of the exact same size. So they all have to be m by m matrices in order to make all this work, otherwise multiplying it doesn't work in how to do it. Oh dear. We may come back to that. Oh, differential equations. Oh, I should have mentioned. I got, yeah. Stuck is always good if you can, at the very least, struggle and feel like you're making some sort of accomplishment. I ended up being bequeathed, the gentleman in question is still alive, but nonetheless, I was bequeathed a set of math books that a professor at one of our local universities was finally giving up before moving into a home. his son, who is my acquaintance. Well, I'm fresh, so who knows? So he was moving into an assisted living facility, and his son was going through all of his stuff and said, Dad, what do you want? And he's like, well, I mean, all of my math books can find different homes, because he had taken none of them out of the box in potentially 20 or 30 years. So he gave them to me, and I started cataloging them the other day. I got a Surface Pro tablet from work, and open an Excel spreadsheet and just started going through. I've completed a box and a half. There are some gems. I told him that if I found anything that was worth, like a couple $100, I'd give him a call, and he was like, yeah, and good luck. Probably not going to find any of them. I'm like, all right, well, you never know. I mean, most everything that he had was like, the 10th printing of the second edition, so I mean, it's probably not going to be worth a huge amount of money, but at the same time, I do want to put that out there, and as in the original Shams, not the mass-produced outline. So I haven't come across any yet, but I've only gone through a box and 2/3, give or take, which was one box that was on mixed DE and analysis, and one that was mostly DE. So I did find a book written by one John von Neumann. I was like, excuse me? I know that name. And I did find a couple of, I found a 4th edition of the Boyce de Prima Ordinary Differential Equations, which I looked at it and I said, that's interesting, because I have the 4th edition of Boyce de Prima, and it looks a lot newer than this one. So the Boyce de Prima that I found, I think, is either like a slightly different title, so technically it's a different book, or it is literally the exact same book. It's just that they waited like 20 years to reprint it or something weird. I don't know. I do know that if it has a slightly different title, sometimes it restarts the counter. So like, I guess, that might be it. It could be that this one is ordinary differential equations with boundary value problems, whereas the one I had in school was ordinary differential equations, or something like that. Either way. We were working on the 12th edition, I think, was coming out when the guy in charge of our differential equations class, the coordinator, was like, nah, screw this. He just went with OER, a completely online educational resource, and decided that it was free. Free was a good price. It was also a little weird when the like 8th and 9th edition started coming out, because Boyce was dead. You know, we'll just keep reprinting the exact same thing over and over again. The other guy will make some changes. That counts, right? I mean, as far as anyone was concerned, that was like the gold standard. You know what? I don't think it was the 4th edition that I had. I think it was 7th. Yeah. Okay. So I think it's 4th that's in his books, and 7th is the one I had. 10th is the one I have in my office. Anyway. Anyway, Yeah, so I have 9 more boxes to go. I spent a good 4 hours on the 1 2/3 boxes that I have gone through already. The others are a bit smaller, so maybe this will go a bit quicker, but at the same time, yes, that is what I said. I have a feeling that I'm going to find a bunch of books that are just mass-produced, everybody has them, and whatever. And so I will gift some of those, I think, to either students or whoever over the years. I need to clean them because, oh my goodness, there's so much dust. I was thinking about wearing one of my COVID masks down there to stop the large particulate anyway. The other thing I was thinking was, ask around at the couple of engineering libraries that are nearby and see if they have any particular need. Give them the spreadsheet and say, do you want any of these? Please let me know. Like, they're all in decent condition. So, they've been read like 3 or 4 times and then put into a box somewhere. Not that I would be doing any of that with my own books. No. Alright. Whew. Bubble. Alright, so, given the matrix that we had here, A11, A12, A21, A22, we want to find the inverse for this. So, if we just generalize it, now this might be psychotic. Let's go for it. So there's a couple of different ways we could do this. One is to say that, we started with this whole concept of like A times I is going to be equal to A, and then by using either a left or right multiplication for identity matrices and for inverse matrices, then we can end up doing a left multiplication. Technically, this is associated this way, equals A inverse A. And over here we have A inverse times A. We can reassociate times I is equal to A inverse times A. Okay, likewise we could do the exact same thing on the other side. I guess here, right? So let's say that this is going to be I times I, and that's just going to be I. Our identity matrix is equal to the thing on the right. And then we could also do the other way around, where we can reassociate this as well, this isn't really association, but I times A is going to be equal to A. And then likewise, we could do a right multiplication of inverse matrices. And again, reassociate. Seven by 7 row reduction, not by hand. That's what the RREF button's for. Yeah, generalizing this is probably going to be hard enough. All right, standard matrix multiplication, we're multiplying the first row by the first column, so A11 times A plus A12 times C. Over here we got A11 times B plus A12 times D. Down here we got A21 times A plus A22 times C. And down here we got A21 times B plus A22 times D. This is equal to 1001. So now we have a well, really it's two systems of two equations, each having two equations and two unknowns. So it's two separate systems of equations. It's not actually like one gigantic system of equations with 4 equations and 4 variables. Oh yeah, no problem. Thanks for coming by. Hope you have a nice night. Data science, woo! I still have to publish my courses. That is not happening tonight. Deadline's tomorrow by midnight. It'll be fine. Now you will notice that I did say, you know, 2 equations, 2 unknowns. Technically the idea is that we know what the A matrix has in it. So A11, A12, A21, and A22 are known values, whatever they might be. It's just that right now, for this exact moment in time, we're saying we don't actually know what the letters represent, but they're going to be given values. And A, B, C, D in the inverse matrix are going to be given in terms of those A subscript values. Well, if we're going to do it that way, we'd better actually do it that way. Whoops. Yeah, I was treating the A subscript values as the variables in this case. Alright, so A21 times A plus A22 times C is equal to 0. Okay, then second system, A11 times B plus A12 times D is equal to 0. And A21 times B plus A22 times D is equal to 1. Alright, so now if we're going to treat this like a system of equations, alright, this is how we work out this particular system of equations algebraically. We say that here we want to get rid of our a's, for example. So if we're going to use the elimination method and say we're going to multiply our top one by negative a21. Let's make it positive. It's arbitrary at this point, but just cuz. And the bottom one multiply by negative a11. Alright, so with this coming in, we've got a11, a21, a, plus a12, a21, c is equal to 1. And down at the bottom, we've got a negative a11, a21, a, minus a11, a22, c. Equals 0. Top one. A21 is that last one there, not 1. Alright. And if we want to add these things together, alright, nope, I can't do it. I gotta get rid of this one. This track's gonna kill me. It was the pitch bend. I couldn't do it. Alright, this first one here is going to go away. Nothing there. This second one here is going to have c as our common factor. 0 plus. Inside here we've got a12, a21, minus a11, a22. Alright, and then is going to be multiplied, or is going to be equal to a21. So here we have that c is going to be equal to a negative a21 over a11, a22 minus a12, a21. That should start looking familiar. And if that's c, then we should be able to plug back in and get a. So we can go all the way back to the beginning, and let's just do this one here because it's got fewer terms. It's got a 0 in it, makes it a little bit nicer. So this is going to be a21 times a, and let's move that. Nah, that's fine. We'll leave it where it is. Plus a22 times c is negative a21 over a11, a22 minus a12, a21. Equals 0. Alright, move that to the other side. a21a is going to be equal to a22, a21 over a11, a22 minus a12, a21. Okay, and then both sides have an a21, so that can go away. And now a is equal to, you know what, that's a terrible idea. A is now equal to a22 divided by a11, a22 minus a12, a21. Alright, 2 down, 2 to go. So we're going to do the same thing here. The only difference is that the 0 and the 1 are exchanging places. So that means that the A21 here is instead going to be a negative A11 on the bottom. So here, oops. That's just going to be the other equation. So we're going to end up with A11, A21, A plus A12, A21, C, except this time it's B and D, right? Not A and C. B plus this stuff, D, equals 0. And then down here it's going to be a negative A11, A21, B minus A11, A22, D is equal to negative A11. So here this is another 0 plus here this is now going to be D is factored out, and we get A12, A21 minus A11, A22. This is exactly the same as the previous one we had. Just, D instead of C. All right, equals a negative A11 over here. Well, now you notice that this thing, A12, A21 minus A11, A22, we can flip the sign on it and flip the sign on the other side as well. So D is now able to be equal to a A11, positive A11 divided by, change the signs, positive A11, A22 minus A12, A21. Right, and then plug that back in. Another one with 0 again. This is going to be A11, A21B. Plus A12, A21 parentheses. A11 divided by A11, A22 minus A12, A21 equals 0. Right, so again we want to solve for B, so move the other thing. B times A11, A21 is equal to a negative A11, A12, A21 divided by this thing, A11, A22 minus A12, A21. Oh, you know what? I didn't go far back enough, but it's fine because it's all the same stuff. So A11, A21 are gone. A11, A21 are gone. So get rid of both these things, and now we're left with B is equal to a negative A12 divided by A11, A22 minus A12, A21. Alright, so now you notice that all four of them have the same denominator with some manipulation of the negative and the value for C. And again, we can just change this around a little bit here, and we say that was a terrible idea. Don't take it off the page. Our A inverse matrix is equal to our ABCD, like we said before. All of the values in here are constants, so constant multiples can be factored out, which means that we've got a 1, over A11, A22 minus A12, A21 times the matrix. A is A22, B is negative A12, C is negative A21, and D is A11. Now this might have a more familiar formula, if you just happen to notice, right? This is equal to 1 over the determinant of the matrix, A11, A12, A21, A22. Multiplied by this matrix, which is now a bit new. In a 2x2 matrix, it's pretty easy to see that our top left and bottom right along that main diagonal just exchange places, and then the opposite two change signs. This is not the case for a 3x3. I don't really want to solve a 3x3 system of equations like this. We could do it by using augmented matrices in that format. It's abbreviated, it's a little bit easier to work with, and it's just matrix operations, which again are the exact same things as solving the systems of equations, what I just did here. Right, and something really important, the determinant of A cannot be 0 because we're dividing by that value. Right, so the determinant of A, A11, A12, A21, A22, determinant is going to be the product of the main diagonal, A11 times A22, subtracted by the product of the off diagonal, A21 times A12. So that's what we got here. Be it slightly different order. Whatever, it's all good. So again, by doing matrix operations and solving the system of equations by row operations, it's a little bit different, but it's not hard. So we were saying earlier that we had this A11, A12, A21, A22 matrix that was multiplied by our unknown matrix ABCD, and we were getting 1001. Now this works with any result matrix as long as the shape of the matrices works out fine. You can get any result. So I could change that to be like 1, 2, 3, 4, and we would figure out what ABCD would be as a matrix in order to get A11, A12, A21, and A22 to become 1, 2, 3, 4, or anything else we feel like. The only reason that we're doing 1001 is because that's the identity matrix, and we're trying to get the identity by multiplying two things together, so therefore one is the inverse of the other. So again, we have a we have A, we're looking for what is A inverse. The augmented matrix is going to be A11, A12, A21, A22, augmented 1001, or again, whatever you've got over there. We abbreviate the A inverse matrix because basically that's just implied. Now what we're trying to do is, effectively, if we can get the identity on the left-hand side, then we're saying that the identity times A inverse is going to be equal to some other matrix, some other result that we're going to get at the end. Now, we should get the exact same thing that we did over here. Shouldn't be surprising. All right. So first thing we want to do is get rid of that. Right, the A21 that's in the second position here, we want to clear out the entire row below. Well, I mean, it's not like super easy, but 2 curves, yep. Good evening and welcome. So Blaine, it's not, I mean, it's not entirely simple, but at the same time, it's also not terribly difficult. If you know how to do it algebraically, you could just do it algebraically. So again, all this stuff that we did back here was just showing how matrices, like a matrix product, is just a system of equations. So in this particular case, we have 4 equations, 4 unknowns. It might be, but at the same time, remember, it's not. This stuff is things that you would need to look into more deeply if you were the one who was, researching them or whatever. Okay, so if we have this, then we're going to say we want to get rid of the A21. Okay, so to get rid of this, we need to then say we're going to just take A11, A12. We're not going to change that yet. What we are going to do is we're going to say we're going to take this row here, and we need to multiply our first row by, we need to get rid of A11, and we need to get A21, and it needs to be negative. Oi, can you even see that? Not really. Okay, and then we're going to add that to row 2, and then put it back into row 2. So when we do this, we're taking the stuff in row 1, A11, we're dividing by A11 and multiplying by negative A21. So this makes a negative A21. Then we add it to A21, so it's going to become 0. On the next one over, we take this thing, we say A12 is now going to be multiplied by negative A21 over A11. This, so that's just what it is. Unfortunately, it's not going anywhere. And then we're adding it to A22, so this is going to be A22 minus A12 A21 all over A11. Gonna fix that a little bit later. All right, so in the fourth one here, we're doing the same deal, but the problem is that R1 has a 0, so we just get row 2 is a 1. Makes it way easier. Okay, and then here in the second row, first column, it's going to be a negative a21 over a11 times 1. So just that fraction plus row 2 is 0. So it's just that fraction. Negative a21 over a11. Very good problem solving. Alright, so then this one, we're going to take that crazy thing there, a22 minus a12 a21 over a11. So take this crazy fraction, multiply it by a row. Oops, wait. No, 1 over that. So we're going to take row 2 and divide it by that thing and then store it back into row 2. Take the whole row, divide it by this thing. That's really nasty, but it works. So, a11, a12, 1, 0, 0. This is now going to become a 1. Down here, we're now dividing by this whole thing. So it's a negative a21 divided by a11 times the quantity, a22 minus a12 a21 divided by a11. Alright, and then second row, second column here is going to be 1 over that thing. Making sure I didn't miss anything here. a22 minus a12 a21 over a11. Alright, so this is now complete, the bottom row, because now we have a 0, 1, which is how our identity matrix looks, right? 1, 0, 0, 1. So the bottom row is complete. This is not very cleaned up, so we're going to do that on the next step when we do stuff with the first row. Maybe we should just do it now. Go chat GPT. Sometimes you just need things to bounce ideas off of. Alright, so if we take this is going to be a11. What we want to do is, no, just clean up first, never mind. a12, 0, 1. Augment, 1, 0. Okay, and then here, you notice that a11 at the bottom can just multiply into both of these things. So this is going to be a negative a21 divided by a11 a22 minus, this is now going to be a12 a21 times a11 divided by a11. So both of those are going to knock each other out. Alright, and in this case, we don't have anything really to do, but the compound fractions kind of bother me. So we multiply both top and bottom by a11, and we can get a11 divided by a11, a22, minus 22, minus a12, a21. Okay, so on the next step, what we're going to do is we're going to take this here and knock out this term here. The 0 on our first column is going to do nothing to the first row's first column, and then the second row's second column is going to knock out the a12 here. So we're going to take negative a12 times row 2 plus row 1. Start back to row 1. Yeah. Well, we ended up with actually, the same guy I was talking about who dropped off all his dad's math books was talking with ChatGPT with his son, who is also a mathematician. And the two of them, he should probably have first dibs at these. Anyway, he was talking with ChatGPT and ended up getting it to admit that it had lied to him about something earlier. And he was like, you take back what you said earlier about this thing? And it was like, yes, I was mistaken. Let me rephrase that. Let me rework this idea. And it was just kind of ridiculous. Rather interesting. Differential equations will scale outside of its ability to be solved very quickly. Linear algebra, I'm not so sure. Yeah, that's also true. You can solve 2x2 systems of differential equations using matrices. It's not actually that hard. And in fact, if you're just doing a second order differential equation at all, you're already doing it, you just don't know it. So if you have, y double prime plus y prime plus 3y equals, I don't know, 2, something like that. Yeah, just ask Georg Cantor. If you get, well, let's just do a 0 because that's actually, right, make it homogeneous. It'll be a little bit easier. So if you come up with a differential equation like this, you can have this just be, oh, I'm going to take a second order differential equation. I'm going to say, let y be of the form c times e to the rt, which means that y prime is going to be equal to c times r e to the rt, and y double prime is going to be equal to c r squared e to the rt. Right, so this is one way to solve it. You come through and you say, if I plug all these things in, this is going to get me c r squared e to the rt plus c r e to the rt plus 3 c e to the rt is equal to 0. Well, if we do this, this creates what's called the characteristic equation. So if you know that the characteristic equation is formed by this, you can say, well, what are my values of r which are going to give me this equation? Well, here we've got a c in every term, so we can just divide it out. It's r squared. E to the rt can be factored. Oops. Yeah, whatever. And then we just get r squared plus r plus 3 is equal to 0. Okay. Well, no better time to learn than now. Right, so when we look at this, we could say, all right, e to the rt will never be equal to 0. This is now a zero product property. So this is not equal to 0, so we can just divide it out. So we're left with r squared plus r plus 3 is equal to 0. Okay, well, that's a quadratic equation now, so we can just solve the quadratic equation. You gotta read some of the calculus history that's out there. It's really cool. Although today, yeah, certainly a lot more people than did 100 years ago. Not everyone or no one? How can I be so good? I gotta tell you, I am not actually that good. The only reason that all of this works here is because I've done it so many times. And, you know, that's really the key to success in like anything, is just keep doing it over and over and over again. And don't satisfy yourself with just like half knowing it. Just like go into it, struggle with math, struggle with it intentionally. Yes, I know. It feels daunting, it feels scary. When I taught Calc 2 for the first time, I was so scared. I'm teaching it again now for the 5th, 6th time, something like that, this semester. And I really do like it. It's just a matter of like getting all the integration rules kind of sucks. But I'm gonna try to get my students to like try and figure stuff out more. I feel a little bad because I don't know if I can do the Peter Liljedahl stuff in Calc 2. It's such a tight class. I have to be very careful how I do it. And letting them just kind of like run off and explore. That's the other thing about Sunil Singh, is that he said that the entire concept of like falling behind is just a myth. We've got to stop doing this. We've got to stop pretending that falling behind is an excuse for, you know, doing lecture basically in class. So I decided last semester I definitely was not going to do any more of my classes as like very stand up front, do a problem, even asking my students like what's next, and getting them to walk through a proof or something like that. Like it got them thinking, but not in the way that I wanted them to, because they just couldn't do anything. And then, you know, 2 weeks into the semester, nobody listens. Yeah, 100% asynchronous classes are like the fully online classes. Those actually take more work, not less. So if your teacher is doing less work than like the in-person classes, they're doing it wrong. They need to be spending a lot of time working with students and talking with you and pulling you into like Zoom sessions or whatever to talk with you about how you're doing and what the problems are. And you know, some of the onus is on the students. You have to go to student hours, or what they call office hours. You have to go if you are struggling even the slightest bit. You have to go. So I'm going to make an assignment for all of my students that they have to come and see me in office hours for at least a half an hour. Right. Yeah, you told me. Well, maybe she's working on it soon. Anyway, so this thing ends up being that c times e to the this stuff, negative 1/2 plus I root 11 over 2, parentheses t, or y is equal to c times e to the negative 1/2 minus I times root 11 over 2 times t. Well, find somebody else's videos on linear algebra. Oh, yeah, I gotcha. Let's see. Who else? Who's this guy? Dr. Trevor Bazette appears to have a full course in linear algebra, 82 videos. I'll post it in a second. I mean, you got Khan Academy, so some of his stuff is some of his stuff's like the very earliest that he ever put on. Yeah, MIT OpenCourseWare is a good one. If you go to like their site, it's usually better than YouTube. Gilbert Strong. Okay. Yeah, that one. Uh-huh. Okay. Okay. So, I see. That's not all him. Interesting. Here's the other one. So it looks like he has a couple of lecturers who are working for/with him on this. Oh. Oh, yeah, I see. Yeah, he aged quite a bit. It looks like the original OpenCourseWare was like 2000. And he has like wow, okay. Anyway. So, interestingly enough, right? What happens here is that, well, first of all, we've now got complex exponents to our exponential e, which then we can change, but also we have two different sets of solutions. So one of the ways that we can resolve this is by saying that, okay, our total overall thing is going to be a linear combination of the first one and the second one. And don't worry about the subscripts, it'll get fixed in a minute. I don't want to use 1 and 2 because those are just easier to end up working with here. Sorry, these are dummy constants, so right, y is equal to. All right, so here we get CA times. This could be also e to the negative 1/2 t times e to the I root 11 over 2 t. Plus c sub b times e to the negative 1/2 t, whoops, that's supposed to have a t there, times e to the negative I root 11 over 2 t. Right, so if we do this, the e to the negative 1/2 t on both of these is common, so that could just come out. Alright, then here we've got c sub a times, alright, this stuff, e to the I times root 11 over 2 times t, and then the negative version of the exact same thing. Well, this is, if you remember your exponential form for Euler's formula, right, e to the I theta is equal to cosine of theta plus I times sine of theta. So here, your theta is going to be root 11 over 2 times t and negative root 11 over 2 times t. So here we just get the cosine of root 11 over 2 times t plus I sine of the same. Okay, there's 1 plus c sub b times quantity cosine of negative root 11 over 2 times t plus I times the sine of negative root 11 over 2 times t. So here, this is going to be y equals e times 1 half t times the quantity. Here, we've got this cosine bit here and this cosine bit here. They're the same thing. The cosine of negative theta is just the same as the cosine of theta because, again, cosine is an even function. Cosine of negative theta is just the same as the cosine of theta. So this thing and that thing end up reinforcing each other. Yeah, trig can be difficult. CA plus CB is now multiplied by the cosine of root 11 over 2 times t. I mean, hell, it took me 15 years to really delve into trig as good as I have it now. Yeah, I mean, I knew it was a function. Alright, now this is something that I absolutely hated. Was that now that we have all these here, CA plus CB and CA minus CB can just be renamed as constants. Oh yeah, they most definitely will. Because all of our electrical signals are passed through as sinusoidal waves. And there's all sorts of fun / weird stuff. If you connect some sort of item, like plug it in or turn it on, the electricity in the system will end up doing or having a like damped trigonometric function. So a damped sine curve. It'll end up having an overpressure and then an underpressure and an overpressure and an underpressure, and still slow down to zero, equalize among the grid. It is sort of an analogy, but it works. So here, right, CA plus CB, we could just rename that C1. And here, I is also a constant. I hated this part. We could rename all of this to be C2. So y can be equal to C1 e to the negative 1/2 t times the cosine of root 11/2 times t plus C2 times e to the negative 1/2 t times the sine of root 11/2 t. Yeah, so like I said, I absolutely hated this idea. The fact that I'm now taking, are you serious? I'm just taking I and just calling it a constant and that's it? Now we've got two things which look like real numbers, but actually C2 is imaginary, so but it's still technically a real valued function? What? I was really upset by that. Yeah, so technically C2 is imaginary right now, but then you just say, yeah, you know, the other constants could have been imaginary, which then multiply times I to make it real. Ta-da! It's like, no, but then the other one would be imaginary. Anyway, it's also possible that CA and CB could be conjugates of each other, which would also fix that problem. Sort of. Anyway, it doesn't particularly matter, but this is, yeah. So we get this some linear combination of those two possible answers to be this. Okay, so that's one way to solve this. The other way to solve it is you say, well, I could take the original equation, y double prime plus y prime plus 3y is equal to 0, and let y prime equal v. So this is like, this is the algebraic solution, whereas this one here is going to be a linear algebra solution. So if y prime is equal to v, then this thing up here ends up becoming v prime plus v plus 3y is equal to 0. That can't be right. Hang on. Maybe it is, and I'm just forgetting. I mean, I have it right there, so I should probably just look. Oof. This is so messy. Woo! Had it right on the side. This is fine. Alright, second order. Alright, so I've got second order system here. Doing this right in my head. Okay, so yeah, I'm also looking at my homework solutions rather than the class notes, so that might also affect part of this. It's okay, it's fine. Alright, so this isn't going to work. No, okay. So this is v prime. Plus v. Plus 3y. Okay, so what we want is something with yv prime is equal to what times yv? So how many y's and how many v's of each do we have to get y prime and to get v prime? So to get y prime, okay, yep, okay, I think I got it now. To get y prime, we just need a v. We need 0 y's and 1 v. Right? Yeah. And to get v prime, that's y double prime, which is the same as the negative of these things, because you could shift that over to the other side. So it's going to be a negative 3y and a negative 1v. Okay, that's good. As long as you were writing it with your own hand, it doesn't matter if it's, you know, permanently on paper or if it's okay. So y prime v. V prime is equal to negative 3y minus v. Okay. So in the linear algebra solution, what we're looking for is a basis. And the way to construct that basis is to find the eigenvectors for this particular matrix, 0, 1, negative 1, negative 3. So what are the vectors, y, v, that are going to return the same value for the derivative as if we had just multiplied by a constant multiple instead of multiplying by a matrix yv? So a times our v is going to be equal to a times some lambda, which again is our eigenvalue. Eigenvectors are usually written as xi, which is always fun because nobody knows how to actually draw it. So just get everybody to scribble on the paper a little bit. Yeah, one sec. Anyway. So what are the vectors xi, which are going to return the exact same value as if you had just been multiplying by a constant value, lambda, eigenvalue? So the way to figure this out, again, is to say that, well, if we do the determinant of A minus I lambda and set that equal to 0, that should allow us to figure out what our values, eigenvalues, lambda, are going to be. Right, not 2, because my lambdas often look like 2's. So in this particular case, we're going to get a 0 minus lambda, determinant, 1, negative 3, negative 1 minus lambda, and set that equal to 0. And that's going to say here, we're going to multiply these two here, which is going to be the same as lambda and multiplied by lambda plus 1. Okay, and then minus a negative 3 times positive 1 equals 0. So here, lambda squared plus lambda. Here is a plus 3 is equal to 0. Oh, would you look at that? It's the exact same thing we had all along. Right, so this is the characteristic equation. Which is the exact same thing as the characteristic equation that we got in the algebraic solution, which means that the eigenvalues are going to be identical to the solutions to the characteristic equation up top here, are negative 1/2 plus or minus I times the square root of 11 over 2. And then if those are the same, then we can plug them back into here and find out what the eigenvectors are going to be fairly easily. This one's kind of annoying just because it is complex, but yeah, well. So lambda is equal to a negative 1/2 plus or minus I times the square root of 11 over 2. So this is going to be a negative of the lambda that we had. Let's just do the fully negative one first so that when we take the negative it will turn positive. So this is going to end up being a 1/2 plus I root 11 over 2. 1. And a lower negative 3. And here, again, that's going to be this same stuff, but then minus 1. So this is going to turn this into a negative 1/2 plus I times the square root of 11 over 2. And the other property of this is that when we take the eigenvector and multiply it by our A, then again we're going to get the exact same thing as A multiplied by the constant itself, which we can alter this to say, look, A minus I lambda as a whole, the determinant is equal to 0, which is going to mean that if we multiply this stuff times the eigenvector, then we're going to end up getting 0. a zero vector. So all zeros in it like that. Y'all are gonna let me get away with that, are you? I don't know if anybody saw that hand waving in real time. Yeah, that's what it does. Seriously, don't let me get away with that. And quite frankly, I've never actually tested this, so... Alright. That's totally a C. Yep, 100%. Okay. Alright, so to be proven. This thing times our actual eigenvectors is going to get us a zero vector, so let's try it out. Again, never tried this before. Could crash and burn entirely. So we have our A minus I lambda, and we're multiplying it times C, and I'm purporting that this is going to get a zero vector. That's what we've been doing with all this stuff the whole time. It's just that, you know, never actually proven it. So here, we can use right distribution to say that A times C minus I times lambda times C is going to be equal to a zero vector, allegedly. A times C, getting kind of close there, aren't I? A times C is going to get us A times lambda by the definition of eigenvalues and eigenvectors. Okay, minus this identity matrix doesn't really need to be there because, again, I times C is... Okay, first of all, I'm allowed to multiply I times C because lambda is just a constant, so we can multiply it anywhere we want. Doesn't have to be anywhere in particular. Yeah, in fact, most people write it lambda I instead of I lambda. Whatever. So I times C is just going to be C. But we need that in order to have them be the same size. Okay. That's why that belongs there. That is not what I wrote. Oh, wait. Interesting. Those aren't the same size. Okay, well, I did something wrong there. Hang on. No, that's why. I did that completely wrong. So it's not A times xc. It's xc times lambda. Or sorry, A times... It's not A times lambda, it's xc times lambda. So, let's fix that. Right, the transformation being done is linearized. Essentially, it's just going to be along that dimension, not over an entire... not some sort of other weird rotation or what have you. Okay, so A times xc is going to be the same as xc times lambda. There we go. Okay, so xc times lambda minus I times lambda times xc. I times xc is just going to be xc, and then lambda is going to be xc lambda, lambda xc, whatever we feel like. Right, because, again, that's going to work. Okay. So proved. Okay, so A minus I lambda times xc is now going to give us a 0 vector. So we do this, and then we say, based on what we've got, we want this to now do the same thing that we did before, where we get a get an identity matrix. Now, it's actually not going to work because our eigenvectors are going to be linearly independent of each other. So we should not end up with a solvable system of equations. Right? This should be unsolvable. It should be you should have a free variable. So that means that this is going to be parallel. No, right. These two lines are on top of each other. So we only get we only end up getting one equation and two unknowns. All right, let's multiply everything by 2 because that just makes it slightly easier without the fractions. So this is 1 plus I root 11, 2, augment 0, negative 6, negative 1 plus I root 11, augment 0. And let's also take the top row and multiply it by the complex conjugate of whatever we got here. So this is going to be 1 minus I root 11 all times row 1, store back into row 1. So when we multiply these, we get 1 plus and minus I root 11, and then here this is going to be a positive 11, so 12. And here this is going to be a 2 minus 2I root 11. But it's not, because here's the thing. The first and the second equations are just linear combinations of each other. That's literally just multiplied by, well, -2 in this case. But if we say take 2 row 2 plus row 1 and then store it back to row 2, well, it turns out you end up with, right, 12, 2 minus 2I root 11 augmented with 0, 0, 0, 0. That's fine. So that's actually not painful really at all. So this now says that 12, usually do like x1 or something like that, plus parentheses 2 minus 2I root 11 x2 is equal to 0. Right, so x1 is going to be equal to, this stuff can come over here, and then we divide by 12. So this is now going to be 2 divided by 12, and it's now negative 1/6. This was negative, now it's going to be positive. Right, positive I root 11 over 6. And this is all times x2. Yeah, and like I finally understand this, at least this bit of linear algebra. Finally really understood it probably about 5 years ago. So it was like just before pandemic, I was teaching this particular math class, you know, our differential equations class, and something clicked, and I swapped 2 of our units and put the linear algebra unit first, and then did our second order systems of equations second. It didn't actually affect the student performance or anything like that, but it was kind of a, like, it was kind of a better intro. So I don't really know quantum mechanics. I know like the fake quantum mechanics that are in Outer Wilds. Okay, and then here we let x2 be equal to just some t. That's our free variable. So x1 is going to be equal to -1/6 plus I root 11/6 all times t. You know, not really. We don't really have, like, we have streaming services, we don't have Netflix, which is really where, like, a lot of the shows that I want to watch are, but at the same time, like, we just don't feel like paying for yet another thing. At least, not for now. Most of the time, the stuff we do want to watch will come out on one of the other services, like, you know, a year or whatever later. How is that? I really want it to do well. Yeah, there is all sorts of crazy stuff that fungus can do. Might be. Alright, so then here, our solutions end up becoming y equals a linear combination of the eigenvector times e to the it's not I, it's eigenvalue, lambda t, lambda 1 t. All right, so linear combination of these things, so therefore C2 e to the lambda 2t. That's the other thing about C is I never draw it the same way twice, like ever. So in this particular case, we got y equals C1 all right, our eigenvector that we got over here is does that t come with it? Seems like it should. Anyway, -1/6 plus I root 11/6 and 1 e to the lambda 1. It's again going to be our -1/2 t plus. No, this one was minus. And it does actually matter which one's which. All right, minus I root 11/2 t. Yeah, it is t. Okay. Here I was worried. Oh, no, no, no. Okay, okay, okay. The vector itself just uses the constants. The t itself does not exist in this particular setup. So lambda is going to be that value here, and then times t gives it to each of the pieces, and then this is going to transform into both our cosine and sine again. And then we put all the real stuff and all the imaginary stuff together and do the same thing that we did before. Yeah, so we can do all the same stuff we did before. We put the real stuff and the imaginary stuff together. We call C1 all the real ones, so all the real ones go together, and then C2 is going to be all the imaginary ones, so the imaginary ones come together, and then C2, again, because it's a real valued function, you just say, alright, well C2 is an imaginary number, so then it multiplies by our imaginary stuff, and there go the i's. So it's all real now. Again, I kind of hate the explanation, but that's kind of how it works most of the time. Okay. So with that, if we go the other route, this is going to be 1/2 minus I root 11 over 2. 1 augmented 0. -3. So this is a 1/2, and then we subtract 1 from it, so it's still a -1/2 minus I root 11 over 2. So then if we multiply this again by the complex conjugate of what it is, which is 1/2 plus I root 11 over 2. This ends up being 1/4. Pluses and minuses all cancel out here, and then here we get this times that. It's going to be a negative times I squared is going to be a positive, and this is going to be 11/4. So just 12/4, so it's a 3. And then here, this is going to be a positive 1/2 plus I root 11 over 2. Here's going to be a -3, here's going to be a -1/2 minus I root 11 over 2. So this stuff is positive 3, and this is exact opposite, so we just add row 1, row 2, and then store it back to row 2. So this is going to be 3. This is going to be 1/2 plus I root 11 over 2. This is just 0, 0, 0. And again, we can multiply this by 2, makes it a little bit easier, gets rid of the fractions. So this is going to be 6, this is going to be 1 plus I root 11. So again, this is going to be like 6x1 plus parentheses. God. Memory's filling up apparently or something. I don't know. Hate it. Six x1 plus 1 plus I root 11. X2 equals 0. X1 is equal to negative 1 minus I root 11 all over 6. So then that's going to get us same. Yep. Identical, it's just the complex conjugate. C2 is going to be negative 1/6 minus I root 11 over 6. 1 e to the negative 1/2 t. This is going to be plus Yeah, I knew I overlooked something. There's another E power in there. No, that's not it. That's fine. E to the negative. I have to. Which again, C1 plus C2 and C1 minus C2 could be renamed to just C1 and C2. That's how we end up with that. This eigenvector needs to be over there too. Yeah. All right, Penn Center asked one earlier. Y prime is equal to x minus y squared. A show y to the fifth is equal to a it's fifth derivative, not a y times fourth derivative of y plus b y prime y triple prime plus c y double prime squared. Right, so fourth derivative. Taking the derivative derivative of each of these pieces, so that this one is going to be a negative 2 times y prime, y double prime. But minus 2 y times, this one's going to be y triple prime. Alright, minus, this 2 will come down, minus 4, y prime, it's going to be a first power, but then we're going to have to do chain rule, so it's also multiplied by y double prime. So it's going to be a negative 2 times y prime, take the derivative as y double prime, squared, minus 2 y prime, nope, gotta go back here. Right, do the second half. So this is negative 2 y prime, y triple prime. And this one is going to be a minus 2. Derivative of y is y prime, y triple prime. Okay, then minus 2, that y stays the same, and then we get the fourth derivative of y. And then this last one, minus 4, y double prime squared. So that's the first one, and then the second one is going to be a minus 4 y prime, y triple prime. So y prime, y triple prime does actually end up back here with this one. And that one. So this is going to be a negative 2 times y double prime squared. So y double prime squared we also have here, that's going to be a negative 6. Parentheses y double prime squared. And then all these other terms, negative 2 y prime, y triple prime, appears, y prime, y triple prime appears in these three terms. These three terms. That's going to be a minus 6 y prime, y triple prime, minus 2 y fourth derivative. Yep. So if this is what we got for fifth derivative, right, so 1 by 4 is this one, it's negative 2. Okay, y triple prime is going to be here, so b equals negative 6, and c equals negative 6. All right, finding a series representation of a differential equation. Okay, so we assume that this is a power series. So y is going to be an infinite sum Oh, we only need one derivative anyway. It's fine. Jeez. Alright, so with these two, we're going back to the original equation. Say that we got y prime is equal to that thing. Sum as k goes from 1 to infinity of k sub a sub k times x to the x minus 1. X to the k minus 1. Okay, is equal to x minus parentheses the sum of So in order to add these things, that's annoying. One of them is squared. Yeah, Penn Center, you are right. This one's kind of awkward, just... Let's try reversing it. So k equals 0 to infinity for x to the k times a to the k, all parentheses, squared, is equal to x minus sum as k goes from 1 to infinity sum k times a sub k Okay, so I think this means here that we're going to get the sum, when written out, getting squared. This basically means that all of our individual terms are going to have choose attached to them. It's not really going to work, though. That's frustrating. Okay, let's try to redo this one then. I want k minus 1 to be equal to 0. And k is k minus 1 plus 1. Trust me, that's going to be relevant. So I'm going to rename this as something completely different and then reuse it as just k. So let all k minus 1s just be replaced by k. So k is going to go from 0 to infinity. We've got here, this is just going to be x to the k all over again. Then it's going to be multiplied by x minus all this. This is again going to be k plus 1. So for k equals 0, we end up with x to the 0, a sub 0, parentheses, squared, equals x minus. Plug in 0. We get 0 to the k's. No, sorry. X to the 0 again. Whew. So x minus. This stuff ends up getting x to the 0. K is 0, so that's just 1. Times a sub 0 plus 1 is 1. Alright, so now we can solve for a sub 1 in terms of a. We've got a sub 1 here just by itself already. Just gotta flip things around, and I should have just left it the way it was. So this is a sub 1 is equal to x minus, this is just a0 squared. And when x is 0, y is 1, is the original. So we could also have done that way up here. So if y equal, come on, y equals 1, which equals the sum, so k goes from 0 to infinity. Alright, a sub k times x is now 0 to the k. Which is a sub 0 x to the 0 plus a sub 1 x to the 1 plus a sub wow, nope. A sub 2x squared, etc. So when x equals 0, the only thing that we're left with is a sub 1, or wow, a sub 0 equals 1. Alright, so with a sub 0 being 1, a1 is going to be equal to, right, x is still 0 minus right, a sub 0 is 1. So a sub 1 is going to be a negative 1. Alright, so likewise, we can now say when k is equal to 1, we can do the same thing. So x to the first, a to the 1, no, a sub 1 squared. That can't be right. Nope. Well, hello. Loims. Good evening and welcome. My name is Obi-Wan Pez. This is N Simplex Pachinko. We are working on a problem that was set earlier by one of our other math streamer type friends by the name of Penn Center. So this was a differential equation that was here. Y prime is equal to x minus y squared, and then try to find a series representation for it as we went through. I'm thinking that it may not entirely be what it says here. Could be wrong. Well, anyway, welcome. If you have any questions, let me know, and I'll try and get to them as soon as I can. I'm also kind of fading a little bit here, so probably going to be moving on at some point in the near future. But I do math streaming on Tuesday nights, and oh yeah, no problem. I usually do math streaming on Tuesday nights and a game on Friday nights. So currently we're working on Final Fantasy VII Remake, because finally it works on my computer again. I just switched to a Linux box a couple months ago. I also got the Don Corneo Coliseum song stuck in my head all day today, which I gotta say, it's a bop. Oh, no, that doesn't work that way. Oh, it's not only that step, right? It's all of them. So when k equals 1, we gotta have both in there. So this is gonna be x to the 0 times a sub 0. Yeah. Yeah. It's one of the new ones because it wasn't in the original FF7, but yeah, it's got this heavy bass line and some good extra sounds in it and all that. Anyway, it's not important. Okay, this is going to be plus x to the first a sub 1, and then that all is squared. Which doesn't really matter, right? Because if x is 0, then all of it's eliminated anyway. Pen. I think you broke it. There's also the possibility I'm just doing it wrong. Always fun. I mean, somewhat. If y'all rather, right, we can do some pre-calc stuff. That's fine. I'm still gonna maintain that pen broke this. Yeah, it's okay. All right, hang on. Of course it does. Okay. Yeah, this is gonna get broken. So if we do this thing, right, the problem is that normally this is a binomial distribution, and so it'll be based off of a finite number of choices, if you will, in the Pascal triangle type thing. Tonga 9. Welcome in. My name is Obi-Wan Pez. This is N Simplex Pachinko. I mean, if this is the first you're seeing of what I do, then I don't blame you. This is x minus expanded out. This would be k equals 0. It's just going to be x to the 0. 1, a sub 1, plus x to the first, 2, a sub 2, plus x squared times 3 times a sub 3, plus dot 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 out to x to the n minus 1 times n times a sub n, whenever that's going to be. Okay, this is equal to a sub 0 x to the 0. It's a sub 1 x to the 1 plus a sub 2 x to the 2 plus a sub 3 x to the 3 plus dot 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 all squared. This is easy. Okay. Yeah, alright. So we're going to have any two terms are going to be multiplied together because this is a squared thing. Either it's going to select a term with its counterpart in the other set of parentheses, in which case there's only one of those possible things. So we can square any one of them. Or we can multiply any of these times any of those that are not the same, and we'll get two of them because of either we can go in this order like that, or we can go in that order like that. So it's all twos and ones. This is fine. Yeah, this is okay. So if we square any of these, i.e. we multiply it by itself, then we end up with like a sub 0 x 0 squared plus a1 squared x squared plus a2 squared x squared squared, or x to the fourth, plus a sub 3 squared x to the sixth, plus dot dot dot, or in other words just plus, right, a sub 0, a sub 1. There are going to be two of these, because again, you could multiply the 0 from the first set and then 1 from the second, or vice versa. And if we multiply a 0 and a 1, this is going to get us x to the first. Two, a sub 0, a sub 2, x squared, plus 2, a sub 0, a sub 3, x cubed, dot dot dot, plus, this is going to be 2, a sub 1, a sub 2, x to the third power, a sub 1, come on, a sub 3, no, not that last set of parentheses there, but okay, dot dot dot, etc., and so on and so forth until we get to a sub n plus 1 times x So 2 times a sub n times a sub n plus 1 times x to the n, no, 2n plus 1. That says it should always be odd. That's not true. Oh, right, it doesn't have to be two consecutive numbers. else in. Okay. And then that just keeps going on and on. Okay. So then x minus all this stuff means that we're going to get an a sub 1 for the negative a sub 1 for the first term here. Then the second term here is going to be a plus x times the quantity 1 minus 2a2. Plus x squared times 3a3 plus x cubed times 4a4, etc. Right, this is actually infinite, not finite. Oh, these are subtraction as well. Come on. So all of this stuff is equal to all that stuff. This is a big mess, but good news is that it works pretty quickly here. Because if we equate all of our stuff, right, over here we've got a sub 0 squared, right, for k equals 0. Okay, all of the exponents on our x's, where they are the same, their coefficients must match. And the sum of all their coefficients must match on both sides. So this is a0 squared times x to the 0 is just going to be 1. We're going to ignore the fact that we're plugging in 0 to it eventually. Okay, so this stuff oh, that's annoying. Right, okay. Yeah. All the stuff with x to the 0 has to be the same as over here with x to the 0. So here, x to the 0, we've got a sub 0 squared. We can in fact get rid of the 1 because we don't need to consider the x's, as long as they have the same as long as they have the same exponents. Okay, is equal to, over here we've got a negative a sub 1. So a sub 1 is equal to negative a sub 0 squared. Which is, we looked up here, we did, a sub 0 is 1. So therefore, if a sub 0 is 1, this is going to be a negative 1 squared. It's just negative 1. Alright, then with k equals 1. Say on the left, all the stuff that has an exponent of 1 is going to be that right there. So if we take the term that has an x to the first, there was only 1 on the left, because all the rest of the numbers are higher. So this is going to be a 2, a sub 0, a sub 1. Killer King! Oh no. A, B, and C as variables. Interesting. It has been quite a while since I listened to some Shania Twain, but I would, generally speaking, say that she is a good singer. It's just been a while. It's not really she doesn't fall within my style. I liked her songs that came out when I was a teenager. Then they applied the Pythagorean theorem. Yeah, okay. This is equal to the stuff that's attached to just x to the first, so it's 1 minus 2a2. If we switch that around, right, a2 is going to be equal to 2 a sub 0, a sub 1. 1 minus that. Right, move that. So 1 minus 2 a sub 0, a sub 1, all over 2. So a2 is going to be equal to, this is 1 minus 2 parentheses. A sub 0 was 1, a sub 1 is negative 1. All over 2. This is going to be positive, so 3. 2 plus 1 is going to be 3 over 2. So 3 halves. Yep. That's one of the reasons why Python allows you to do that. Call it whatever you want. Make it easier for you. Alright, now the squared stuff. This is where it gets a little bit harder. So here we have a sub 1 squared plus this one. Right, a 0 and a 2 add up to 2, so 2a sub 0, a sub 2. That's set equal to, this one over here is a negative 3a3. And we don't have any more squares that we can get, so just the 2. So here that can move over. It's going to be so that's negative of those. 3 is negative a1. A1 was negative 1 squared minus 2. A sub 0 was 1. A sub 1 was negative 1. 3, which is then going to get us a1. It turns negative, so negative 1. Here this is negative 2 times negative 1 is going to be a positive 2. This one's going to be a 1/3. Yeah, I can do that. Might have to, like, open up something on the side, either like GIMP or Paint. I don't have the Paint, but I might have something. Okay, cubics. Same deal here. We've got one there, we've got one there. So that's going to be 2 a sub 0, a sub 3 plus 2 a sub 1, a sub 2. Oops, that's not equal. That's going to be equal to a sub, x to the third on this side is negative 4 a4. No, I like the idea. I don't know quite how I'd implement it, but it is a problem that is worth solving. Alright, if we divide everything by 2, then we get a sub 0, a sub 3, plus a sub 1, a sub 2. Is equal to negative 2 a sub 4. Alright, a sub 0 is 1. A sub 3 is 1/3. Plus a sub 1 is negative 1. A sub 2 is going to be 3/2. Yeah, nice. This one's going to be 2 minus, this is going to have an extra 3, it's going to be 9, and multiply by 6 on the other side is going to be a negative 12, a4. So simplify, getting rid of the fractions. This is going to be a negative 7 over negative 12 is going to be a sub 4. So a sub 4 is going to be 7/12. Yeah. I'd love to be able to do some cross-disciplinary stuff like that. Alright, so there's A4. Here's A3. Okay, so the way that this works, right now at least, is that now we have a series of solutions which then give us a basic equation, y equals, again, a0 plus a1x is the first, plus a2x squared plus. That's just going to keep going on forever. We, on the other hand, do not have all the time in the world to write something forever, so this is going to be y equals a sub 0 we found out was 1, plus a sub 1 we said was negative 1, okay, so 1 minus x, okay, plus, come on, 3 halves x squared. I was expecting that to be negative, but nope. Okay, 1/3 x cubed. Seven twelfths. X to the 4th, plus, etc. And this is just going to keep going. So at the very least, we got the first 5 terms to the series, and that will help us figure out what the approximation for any of the particular values are going to be for that function. Okay. Yeah, it's about time. Okay. So. Alright, looks like there is yet more Elite Dangerous drops. So those of you who play Elite Dangerous, you can get some drops from Boss Lady B, whom we are going to raid out now and go see. She is one of our good streamer friends. We like to generally go over there and say hi. So thanks everybody for coming. I will be back on Friday for more game stuff, and next Tuesday for more math stuff. At some point, I don't know, I mean not this semester, but maybe in the future might be able to do some extra stuff, but yeah, for now it's gonna stay as just the 2 a week, especially during the semester because I've got enough work that I don't do often enough. Anyway, have a good night, everybody. This is Obi-Wan Pez for N Simplex Pachinko. See ya.